Hey everyone, so this is just a quick follow-up video on the other one that I did where I showed the application running and just doing its measurements. So now I'm going to talk about the setup that was used to make those measurements. So I'm going to get into that, but if you were one of the couple of people who emailed me and said, I think I know what you're going to test, and you said these, you're right, we're going to test these. Now there's a couple of gimmies with these right off. They're bigger. They have more surface area to dissipate heat. Of course they work. I never doubted that for 1 minute that these weren't better at dissipating heat. They're bigger, physically bigger transistors. They have, more thermal transfer capabilities. They have more thermal mass. Of course they're going to work. So that's why I never bothered to even talk about them. It's like, what's to talk about? I mean, do they transform more? Of course they do. So the question really I always had was not the transistor. I never thought that these didn't do the, run cooler or dissipate more heat. Was the test that was being used. Like, it was literally a guy with a microphone yelling into a microphone and using an infrared thermometer and then saying, see, here they work, and then using a radio that had poor heat sinking to start with. So the device used for the test was quite poor, and the yeah, anyway, so this is a 980. It has a similar design to that Magnum one that was used for the test, meaning it has metal sides. Okay, metal is a poor thermal conductor compared to aluminium. Aluminium is far superior thermal conductor, which is why it's used. Copper is better than aluminium, which is why even in a lot of computer heat sinking, you'll actually see a copper slug in the aluminium that's used to contact the part, like a CPU or what have you, usually a CPU, that then dissipates into the aluminium, which is used usually the fins. And that's why we're talking about the really expensive heat sinks using the slug of copper. But the aluminium, it's relatively inexpensive and it's a good conductor of heat, which is why it's used. The radio used was the cabinet designed very, very much the same as this. Metal sides, aluminium back, but no heat spreader for that transistor to mount to sink any of the heat off. So it's mounted right to metal. And this has no thermal mass here. We're talking about a thin piece of sheet metal. So, yeah, we put a bigger transistor in to compensate for the fact that the thermal design of that area, that side, or that whole circuit was poor to begin with. So, of course, it worked. But that was really, if you wanted to fix a Magnum 1 radio, which I don't have one of them, and improve its heat dissipation, that's thermal design, you do what Uniden did. You put a piece of metal aluminum plate in there and move on with life. So why that wasn't done to begin with by the designers beats me. I'm still scratching my head on that one. I don't understand it. So anyway, like I said, do these work? Sure, I don't see why not. But the TIP36, does it, are we going to have any kind of, do we even have a thermal management problem with the TIP36? I don't think so. Maybe in some edge case, but not that I can tell. So anyway, we'll talk about the test setup. So let's look at the test setup and get this camera off the tripod. So we have the radio, and it has the TIP36 in it. We have some thermocouples, not any infrared measurements. These thermocouples go to another instrument. This part is not the thermally sensitive part. That's at the tip, which obviously I'm not going to touch. This is another one over here. So there's one in the air, there's one mounted to the heatsink in the back, there's one in the front of the AM regulator, and there's one in the back of the AM regulator. And that's what these, that's where these two guys here are going. One's going down the one side, one's going down the other. And these are, quite rigid, so, and they're not very flexible. As far as transmitting the radio and injecting the tone, got a jig here for that. So the tone's going to come in. We're going to go into the front of the radio. This is going to control this relay. This is all controlled by a computer. I don't touch anything but a button on a computer, and it triggers everything. RF out of the radio goes into a 20 dB attenuator. And the reason for that, radio makes a fair bit of power. I don't want to damage the CMU 200 here. It can take 50 watts, but this radio can actually put out a bit more than 50 watts. So, you know, your typical, you know, got attenuator in front of it, DC block on the front of the instrument, multimeter, just a 3478A, thermocouple monitor, which is a Stanford Research Systems SR-630, and just an attenuator switch driver, the 11713A. I just have it connected to switch 9, which is in the back. So that's what this is. This is switch 9, and that just runs down to the front of the radio, to that relay. The rest of this is just GPIB cabling. So nothing too spectacular back here, except for all this GPIB stuff. So I'm going to put this camera back on its tripod, and point this thing at the, there we go. So we can watch the temperature as it goes ahead and starts controlling things. So I'm going to go ahead now and trigger the application when the computer wakes up. So here we go. So the radio starts transmitting. That's what that is up there. So it triggered the light. Of course, everything is in remote control. Computer has taken over, and now it's just measuring the temperature. 1 is the air temperature in the room, 2 is the RF, 3 is the front of the AM regulator, and 4 is the back, the heatsink, behind the heatsink. So that's measuring the heatsink directly behind it. So I'm expecting the front of the transistor will get warm initially before the back, and then of course what will happen is as the temperature increases and it starts to conduct heat into the heatsink, the back will overtake the front, which is another reason why you don't measure these things from the front, because the back is always going to be warmer. So I don't have any idea why you would even point a thermal, you know, infrared thermometer at the front of the transistor when the back is the part that gets hot. So you'll see that in the graph that I'll put at the end of the video when the test concludes, what happens there. So, you know, the transistor casing is a, you know, the epoxy is a somewhat poor conductor of heat. So until that gets through to the heatsink, you know, it will rise quicker than the back. So that said, should be almost done, and then that will conclude the test. What I would like to know is if there are any other parameters that anyone would like me to log, if I can. So if I can do it, I will do it. But I've done this for a long time, and it's finally not transmitting anymore. And that's where it pretty much peaked out at. So that's like a pretty warm bath at best. So just, come on, give me local, okay, it gave me local control. There it is in Fahrenheit. Yeah, it probably maybe hit 130 Fahrenheit in those 2 minutes. A far cry from 200. So anyway, guys, let me know what else I should test. Any other transistors or things that I need to log, let me know. Thanks for watching. Till next time.